Okay. Hello, everyone. So this is going to be the last lecture of the deep learning class, and I believe also the last lecture of the whole summer school. So what's the title of the last lecture? It's called mean field. And okay. So, but of course, this lecture is going to connect. We are going to continue where we left it this morning. So I'm just going to remind you of where we ended up. That was this notion that given a nonlinear model, we try to capture how likely this nonlinear model is to behave as a linear one through this notion of a relative scale, right? Which is you can think it as a kind of a ratio between the curvature at initialization and some kind of like a squared Jacobian, right? Like a squared inclination. So can we actually quantify how this a relative scale controls basically how close the dynamics, the nonlinear dynamics, are going to be tracking the linear dynamics? And so the answer is yes. So there's this theorem from the Shiza and Back, Oyalon and Back, 19, which is the theorem 2.3, if you want to look at the reference, that essentially says that assume phi and d phi, the model and its Jacobian are Lipschitz around its initialization theta 0. So I look at consider this nonlinear model, and I consider how it behaves at initialization. So we define theta of t. Sorry. So theta of t is the trajectory of a nonlinear model. Okay, so this is just gradient flow, right? On the right, on the true model. And theta bar of t is the trajectory of the linearized model that we call phi bar, right? If you remember, that was the linearization of the model around initialization. So what this statement says is that then, for a number of time that is controlled by something that depends on phi, so in their paper it's explicit, but here just I want to give you the whole picture. So there's a constant, right? And then for all times below this constant, what we have is that the distance, so if I look at the model, like the nonlinear model, like the functions that I learned, like the trajectories that I do in function space between the nonlinear model and the linear model, relative to the value at initialization, so that's the error I get at initialization. This is controlled by something that is at the order of time squared times the relative scale of the model at initialization. Okay, so here what we are just doing, we are just quantifying, formalizing this intuition that we described this morning, that when this quantity is very small, right? So when this relative scale is very small, the trajectories that I visit using gradient flow on the nonlinear model, they can be very well approximated by the trajectories I would get if I was just considering the linear model instead. Yes?
So this theorem takes us from local to more global, let's say.
Yeah, with the caveat that this is only true for finite time, right? So it doesn't, at this point, the way I formulate it, it's not a statement about uniform in time. But that's a good point. So there's a number of remarks. But the important one, like the punchline here, is that the nonlinear trajectories, they track the linear trajectories. So you can think it that you initialize the model at the two trajectories start at the same point, right? So they define the same function, theta 0. So the nonlinear trajectory would visit some functions, and the linear trajectory visits different functions, but these two trajectories in function space, they're very close, right? And it depends on the relative scale.
We don't know how long it takes to converge.
Right. So at this point, this theorem, basically, but what you know is that in that guy here, you get linear convergence, right? So you don't have to wait a long time before you converge, right? So in other words, if these two trajectories are tracking each other, and this one gets the energy low very fast, this should make you a bit wary that maybe this statement can be extended for infinite times. And that's actually what's done in the paper. So if you look at so you can actually get a uniform bounds, right? So in the over-parametrized regime, these can be made uniform in time. And this is their theorem 2.4. So right, if you look at their paper, the theorem 2.4 is a version that is uniform in time of this one, right, with more assumptions. Yes?
What are you calling over-parameterized regime?
Over-parameterized regime, again, in this context, would be the case where the corresponding kernel is full rank, right? So it has nothing in the null space. Okay. So this is just formalizing what we already described. So now the natural question is, when does this lazy regime happen when we instantiate this theorem in the case where this phi of theta is our neural network, right? And let's try to make this instantiation in the case where the neural network is just a single hidden layer. Okay, so now let's think about a model where we take phi of theta, and again, I'm going to use the x here. I'm going to choose a scaling. So we saw that when I choose here 1 over square root of m, right, and we let m very large, we had the impression that the model kind of behaved like a kernel. In the sense, the kernel converged to some object. Now let's try to put this alpha here as a free parameter, right? So we have g of theta I with x. So let's compute this function, and what I'm saying here is that I'm initializing this theta i's iid from some measure theta 0, and I'm choosing these functions, these neurons, such that expectation under theta 0 of g of theta is 0, right? So in other words, at initialization, the expected value of this function is 0 everywhere. And let's try to now define this scaling, like the relative scaling as a function of m, as an expectation with respect to the initial distribution of the relative scale of this model at theta. Okay, let's see how the relative scale grows or behaves with m. So so in the relative scale, we have 3 terms, right? Let's compute these 3 terms for that formula. So the first term is the distance at initialization between, or initialization and the target. So what does this thing converge to when m goes very large? So this is a sum of random functions whose expected value is 0, right? So this thing is a sum of things that have 0 mean, right? So if m is very large, you can convince yourself that, essentially this thing is going to fluctuate, but it's going to concentrate towards something that is like alpha. F star, right? Because I'm using a zero initialization.
Why did you assume that the expected mean is 0?
You will see, because I mean this is something that will really make this relative scale apparent, right? And in fact, it's a good question. If you look at what happens in practice, right? So typically you initialize this neural network architecture such that for example, let's take as an example. G of theta of x has some output weight times a activation function, like a sigmoid, plus some b, right? Or something like that. So as soon as this output weight is initialized with a zero mean variable, right? This in expectation is zero, right? It's a zero function.
Now you need the alphas to go to zero faster than 1 over square root m, right?
Yeah, that's what you will say. Yes, that will be the final conclusion. Yes, in fact, right? The second point, of course, is just to compute the gradient. So what is the gradient here? The gradient is going to be, it's going to contain the gradient of g at theta 1, and the Jacobian of g instantiated at theta m, right? So if I look at the squared norm of the gradient, so of course here I'm being very sloppy because of course these things you should take into account the fluctuations, right? But I just want to give you the overall picture. This thing is going to behave like what? I forgot alpha of m. So this is going to be, the square norm is going to be alpha m squared times m times the expectation of d of g on theta. And what about the Hessian? So this is going to be a matrix that is diagonal. It will contain alpha of m here. Zero, zero. Correct? So what is the norm of this guy? Again, it's alpha of m times the expectation of yes? So now, if we take these three things together, what do we see? We see that the relative scale essentially has a growth that is 1 over alpha of m times the relative scale of the original function. Right? So the conclusion is that if if alpha m times m grows, right, then the relative scale goes to 0, right? So in other words, you enter the lazy regime, right? So if this thing is actually, so if alpha of m is a small o of m, then we are in the lazy regime. Okay, and so of course, at this point, you can ask two questions, right? At least I think about two questions. First one is this a realistic regime? So if now you go into the real models, right, the models that the people, the practitioners are using, and try to see, okay, is this regime, is this theory matching what they are using? And the second question, of course, is what happens when we are not in that regime? Okay, so the first question, I think, is important, and it's somehow not completely trivial to answer, right? If you look at the standard initialization of these models, I don't know if some of you have been playing around training these neural network models, the initialization typically is normalized in L2. In other words, that the initialization that people use really looks like 1 over square root of m. But on the other hand, what is the conclusion that we get from this theory, right? So if that was true, right, and the real models, networks, were in fact explained by this regime, what we have just seen is that one of the consequences is that parameters, they don't need to move too much, right? Because in a sense, they get to the global minimum super quick, right? They don't have time to move. So if you look at what happens in the real models, when you initialize these big neural networks, in particular on images, they have like this bunch of different filters. When you look at what how the filters look like at initialization versus how the filters look like after training, they have moved a lot, right? It's not, so this is not maybe the whole picture, right? So in other words, maybe we need to do the next step and try to see what happens beyond this regime. So in other words, in particular, there's there's one regime. In fact, actually, this is something I got wrong. Yes. So actually, what I need is this thing. Actually, so if alpha of m now is 1 over m, right? Actually, this has to be 1 over m, right? That's what I have. Okay. So if now kind of the transition seems to be alpha of m being 1 over m. Right, so that's a regime where this thing does not blow up, right? So the denominator does not blow up, and this thing stays of order 1. So that's what we are gonna, how to explain this regime, where alpha m is 1 over m. So that's what we are gonna do in the remaining of this lecture. Any questions at this point? Yes?
So if you said in practice it is around 1 over root n.
Yes.
Then it should be the lazy regime, right?
The thing is that, what happens in practice, there are so many aspects so in practice, for example, if you train a single hidden layer neural network with lots of units, you're not going to get state of the art, right? So it's true that the initialization that you use looks like an initialization in L2, so it looks like 1 over square root of m. But first, you are not making m go to infinity, and then you are using a model that is not a single hidden layer unit, right? So it's not, there's still a gap between, actually what I'm going to, of course, explain is not a full description, but already it addresses one very fundamental, in a sense, problem or limitation of this framework. That is the fact that if that were true, then there would be no benefit between a neural network and a kernel machine, right? This is just one particular kernel machine. Yes?
The relative scale that you've defined also has the distance to the optimum?
Yes.
And you said that, like, in practice, that's often large. So, I mean, are we...
No. So, sorry, the distance to, so I mentioned two notions of distance. One is that you can look at the excursion that you have done in parameter space. So you can look at the parameters at time 0 from the parameters at the end of time. And what you observe in practice, and this is really like something that you can take at face value, is that features move, right? Things move from beginning of training until the end of training. And this, at least, this phenomena is not completely captured by the lazy regime. Okay, so now we are going to move to a different regime, which is, what is the name of this regime? So this is going to be called the mean field regime, right? And we are going to try to get together, try to get like the main ingredients. Okay. So now, our model can be written really as an average of functions. Sorry. Theta I. And so this model contains a bunch of parameters And each of these parameters, you can think that belongs in some parameter space, right? So just taking this particular formulation of before, the parameter, so every one of these, right? So each one of these terms is what I call a neuron. It's a little function, has its own parameters that involve input weight, output weight, bias, etc. So the first thing to observe, right, is that if I go back to the original problem, which is to minimize with respect to this vector of parameters, that is the vector of, like the domain of parameters, that is t to the m of some loss that depends on phi of theta, right, as before. So this problem, in general, has poor local minima. Okay, and this is for any finite m. Okay, and one of the references for this is you can look at the paper by Safran and Shamir. And my student Luca also has a paper, Venturi, Bandeira. So we have also, there's a paper. Essentially, these results basically construct negative examples, right? So you can, for a given architecture, we can define data distributions for which we can provably establish that this function has poor local minima. And the poor local minima are non-degenerate in the sense that they have there's a non-zero probability to end up there. So of course, like the problem at finite m cannot be simple, right? It's not something that we can, in the worst case, this problem can be very hard, right? So in the sense that there's instances of this problem that are hard. So in the sense that this motivates two things is that what happens, I would say, on the typical case. And maybe what happens also for m sufficiently large. So what we're going to see is that now we are going to, in a sense, once we go from a deterministic analysis to something that we are going to introduce some randomness, this naturally will have to use ideas and tools from statistical mechanics, right? And that's what we're going to be hearing about in the last 40 minutes. So let's start simple. So let's assume, again, like a quadratic loss. Again, that this is our favorite loss, quadratic loss. And now let's use the fact that in our case, f is just an average. We use our formulation that is an average of functions. So if we develop the square here and we put the sum here, what are we going to see? That we are going to look at the energy with respect to our parameters, theta 1, theta m. What is this thing? There's one term that is the norm of f star squared. That's a constant. And now what do we have? We have 2 times the dot product between f and f star. And what is f? F is the sum of terms. So what do I have here? I have 2 to over m. The sum from 1 equals 1 to m of the dot product between my neuron and f star, plus 1 over m squared, the cross product, right? It's like the norm of f. And because f is the sum of terms, I can develop, so back here what I'm saying, I'm assuming that this is not a problem, that this is the same as the dot product between f minus f star and f minus f star. And remember, we are using the same convention as this morning. The dot product is the expectation with respect to some data distribution. Okay? And what do we have here? We have the dot product between g of theta I and g of theta j. And here, apologies, I dropped. Again, I'll drop the index on the argument because I hope it's clear by the context. So now we can define a function that I will define it formally as the dot product between a neuron at any generic position theta and f star. And I also define a kernel that is the dot product between g of theta and g of theta prime. So notice here that this is a kernel that is kind of the dual kernel as we have seen before, right? So all the kernels that we have been describing yesterday and this morning, they were kernels that were basically looking at the data, right? They were k of x prime. This is kind of a kernel that looks on the other side, right? Looks on the side of the parameters. So now with these two definitions, we can rewrite the energy that, like the loss that we have as a constant that maybe we don't care about, right? Because it's optimization, so we can just, I will still carry it, but it's not so much important. 2 over m, 1 over m, the force, like this f evaluated at fi, plus 1 over m squared, the sum from I equals 1 to m of the kernel at I and j. Okay, so at this point, I'm going to introduce what in physics or sometimes in physics called like an ansatz, right? Just as a way for us to think differently, is that, so I told you that this g of theta was a neuron, which is, in a sense, it's a function, right? It's a function of from x to the reals, but I'm going to assimilate this neuron with a particle. And the particle, so here it's a neuron that is a function, and this particle now is a particle theta that is somewhere sitting in the space of parameters, right? So now, when we think about a neuron, we can just simplify things a little bit and think that when I have a model, I have a space of parameters D, and I have a bunch of particles, right? So every one of these particles, theta I, is associated with a corresponding function. And what we have here, I mean, at this point, this is just it's not saying anything profound, but now we can essentially reinterpret this loss as basically a Hamiltonian of a system of m particles, right? So here I have m particles, and what this loss is actually modeling is a Hamiltonian of a system of particles that interact. Okay, so in the Hamiltonian, we identify 3 terms. So there's one term that we don't care about, right? It's just a constant. So there's one term that is linear, right? It's like a sum over the particle. So this in physics, if you see this, you would interpret this as an external force, right? You have a force that is f of theta that is acting on each parameter, and this carries a non-interacting component, right? I mean, the force acts in every particle independently of the rest, where the rest are. And then I have another term that is an interaction potential, right? It's like I have a function that is given by a symmetric positive semi-definite operator that tells me how two particles interact with each other. Okay, so now you have to think that when I do gradient descent, what am I doing? I'm taking the gradient with respect to this guy. I'm trying to make the energy smaller. So this in Lagrangian mechanics corresponds to basically you have put some particles there, and you let them evolve through the Hamiltonian, and basically this describes the evolution of a system of n interacting particles, right? So in particular, as you can see, this interaction potential, basically what it does, it tries to push the particles away from each other. Right? So in a sense, you want to make particles that somehow align with the external force, and in a way that they are not falling too closely one from each other. So now, at this point, this is just reinterpreting what we have. But now let's introduce an object that will somehow simplify the whole thing. Sorry?
K doesn't have to be positive.
Say again?
K. The
K.
interaction term.
Yeah, well, it's in a sense because it factorizes as basically a function times its function transpose. So it's a positive semi-definite kernel.
No, but individual entries can.
Oh no, individual entries can be whatever. Yeah. So in the case of ReLUs, you would have things that there is no negative, but it's true for general activation functions. This can have it's arbitrary at this point. So now, how do we study in particle systems, in statistical mechanics, how do we study these kind of systems? So Now, so as maybe you remember or you know from physics, of course, there are many ways where we can see this, but there are two kind of canonical views, two canonical ways to interpret the system of particles, right? So one is what's called the Lagrangian interpretation, where you have a reference frame where you basically track every particle, right? You have coordinates for every particle, and you can follow them, right? And then there's another point of view that is kind of the dual one, that is called the Eulerian point of view, like the point of view of Euler, where instead of having a system of a reference frame where you have one coordinate per particle, you are basically going to lift the problem into the ambient space, and you are going to have one measure for each location and just track what is the probability, what is the density of particles at every given location. So here, the right object, the right way to make the connection is through what's called like an empirical measure. So formally, I can just define it as a bunch of Diracs located at the positions of my particles. So in this picture before, I have particles in this location, so I'm gonna assign them a mass, right? A mass of 1 over m. Each of them will correspond to a little Dirac of mass 1 over m. And so using this formalism, now we can look at that. So this is actually a probability measure in the space of parameters. So this is a probability distribution. So it has mass 1 and it's non-negative. And now there's this interesting property of this object is that now we can go back at our function of x, right, like phi of x, and we can try to rewrite it in terms of this empirical measure. So remember that this before was like a 1 over m, the sum of functions. So how can we now rewrite it in terms of this empirical measure? It's an integration. It's an integral of g of theta x with mu m with respect to d theta. And what is at least at the formal level, you can see that this has a number of advantages because now, so here, this is what's carrying the parameters of the model, right? This is what's carrying what we want to learn. And what is the dependency between this object and the function at this point? It's linear, right? So the function is linear with respect to the measure, right? So, and you can see that this is really what will bring a lot of structure into the problem, right? Because in a sense, everything we have seen is that if there's one lesson to learn is that when you have a nonlinear problem, in order to understand it, something that typically works is to try to linearize, right? Try to transform it into something that produces some linear structure. So here we have it. Of course, we have to pay a big price, right? Because now, instead of having m parameters in this parameter space, now we have an object that, of course, is in a much larger space, right? It's a measure. But there's another important property of this script formulation is that suddenly now we have an object that captures all the invariances of the model, right? So I gave you this function description here, right? So this is parameterized by theta 1, theta 2, theta 3 through theta m. But because I'm just considering an average, a sum of functions, I don't care if theta 1 becomes theta 3 and theta 4 becomes theta 6, right? I mean, the only thing that matters is whether I have a function here or not. And this is captured by the measure, right? I mean, the measure is an object that seems a bit more intrinsic than just having a vector of where the parameters are. Okay? So in general, so of course this is something that we can write for the empirical measure, but as we saw yesterday, you can actually make it more general. For now, you take any measure, right? So for any mu that is a probability measure in the parameter space, you can define this integral representation. And now we can associate a corresponding energy functional, right? So we can define that the cost. So now we can look at the problem, not in the space of functions or not in the space of parameters, but in the space of measures. And what is the corresponding loss? What we then define it as the corresponding, so using f that is defined here. Okay? So if you write it, so now we can do the exercise together. So if we just replace, right? So remember that this is f minus f star squared. And now this f is going to be the integral with respect to mu. So we develop the square. What do we get? We get the same constant as before, minus. now using our formulation, 2 times f of theta mu d theta plus the integral, like the double integral, of k theta theta prime mu d theta prime. Okay? So at this point, the only thing I've done here is essentially apply the definitions, right? There's no step. There's no non-trivial step. So you'll observe something that is interesting, is that now let's look at this energy. Let's look at, we have a problem where you need to minimize this functional with respect to the measure. So I told you that this is a symmetric kernel that is positive semi-definite. So this problem really looks like a easy problem. Like it almost looks like a convex problem, right? Because it's quadratic with respect to mu, and the quadratic form is positive semi-definite. So now you'd say, oh, wait a minute. Does it mean that now I can just query convex optimization and then I'm done with that? Well, the reality is not as simple. And there's something subtle, is that the notion of convexity, it depends on the geometry, depends on the metric in which we define this object, right? So typically in the convex geometry, what you say to say that the function is convex, typically you take to take 2 points, x and y, and you compare f of x versus like f of x, f and y versus the function along a certain path, right? And in the convex geometry, you took a linear path between the two, right? So this happens to be a geodesic in the Euclidean domain, right? So in that sense, indeed, if you take 2 measures and you consider the mixture, like kind of the linear interpolation between 2 measures, this energy functional is convex, right? It's really below its core. But in fact, in the space of measures, there's many geometries. And it turns out that the ones that we are going to be needing is using a geometry that is called the Wasserstein metric. I don't know if you are familiar, but the thing is that this functional looks convex, but in fact, fundamentally, it's not convex, right? So, and in a sense, it captures really the fact that this problem is hard, is complicated. Okay, so at this point, I didn't talk at all about dynamics. So at this point, I just rewrote the model and the laws in terms of this new object that is the measure, the empirical measure. So now let's talk for a second about the dynamics. Okay, so what about the dynamics? So we know that in our making the same continuous time, so I'm working again in continuous time, what we have is that we have what's called like the particle gradient. That is nothing else than the original gradient flow, right? So what we had is that if we stay in the Lagrangian formulation, basically in parameter space, we know that this is every particle follows negative gradient of the energy, right? This is just the original problem, right? We just look at the continuous time gradient descent in the original parameter space. So this, as I said, you can think it as a kind of a Lagrangian perspective. So every particle has a velocity, and you are just tracking the velocity of all the particles. So now what would be the Eulerian perspective? So in other words, in the picture, we have our particles, like theta 1, theta 2, etc. And every theta has a velocity, right? You have a velocity that is given by this object here, right? So what would be the Eulerian perspective? So maybe we can look at all these velocities. We can basically see them as a vector field that is not defined for every particle, but is defined everywhere in the parameter space, right? So we can, in other words, we can actually formally write that by proper scaling, and the scaling is actually not intrinsic, so we can formally see that the particle gradient in fact, can be seen as evaluating a velocity field. Okay, so this V is what I call a potential, right? So like the gradient of V, when I have a potential energy, the gradient of the potential is the velocity, right? It's the velocity field. And what is the corresponding potential? This is nothing else than minus the force plus the integral of k prime mu d theta prime. Okay, so these are, at this point, is a formal exercise, right? You can explicitly compute that in terms of the F's, right? So this energy, it's expressed in terms of the force here, right? In terms of the F's and the K's, right? And it also intervenes, like you can rewrite this as an integral with respect to the empirical measure, right? Everything in terms of the measure. So if I take the gradient of that formally, I can see that when I evaluate this thing for a given, and this is actually the empirical measure, right? So when I evaluate it in the empirical measure, I can see that the particle gradient, have to scale, if I scale all the gradients appropriately, converges. I can see it as basically evaluating a potential over the whole space. So in other words, the particles, they move because they feel that there's a velocity field, right? There's a whole field that is defined on the whole domain, and they feel that. So, in fact, now we end up in a sense, this is a classical problem, right? So now I ask the question: if I have a measure, so I put some mass in that domain, and I let the measure evolve under a velocity field. So basically, if you have a measure, and in that domain you have a velocity field, the mass is going to move. So how can we describe? In other words, how can we describe the evolution of a measure, like probability measure mu, under a time varying a velocity field gradient of v of theta mu t. So this is actually a kind of a classic problem in statistical mechanics, right? In many areas of physics. And this actually is given by something that is called a continuity equation. That is actually a partial differential equation. So it's the partial derivative of mu with respect to time is a divergence of the potential, like the gradient of the potential, mu t, evaluated at mu t. Okay, so I understand that maybe you are not familiar with, like looking at the partial differential equation that involves a measure. So just to give you the main ingredients, and we are not going to be drawn into the technicalities, this is really nothing else than the divergence theorem, right? So basically from like a basic mechanic, basically the application of this theorem, that if I want to understand like the rate in which mass enters or leaves a certain domain, I can apply the divergence theorem, and basically depends on the amount of flux that the surface sees, right? And the amount of flux is basically exactly given by the velocity field. Okay? And so this equation is actually very rich. So it's there's many very profound, like very, let's say, sophisticated math that is put into the analysis of that sort of equation. So here, of course, I have to cite like the papers that basically use this technology in this particular context. And it's actually quite remarkable because there are 4 papers that basically came up with the same model at the same time, like in like a couple of months difference. So the papers are, so there's one by Songmei, Montanari, and Nguyen. So this is in PNAS 18. Then there's another by Leonic, Shiza, and Francis, Nirips, 18. There's one from my colleagues, Grant Rotzkopf and Eric van den Eyden. Also in the ribs. And then there's another one by Sirignano. And Spilopoulos. So in fact, there are many things that we could say about this thing, and but time is a little bit pressing. But in particular, you can interpret this equation as what's called like a Wasserstein gradient flow. So in other words, this equation is describing the infinitesimal behavior of, I have a measure, and I want to minimize the energy function. So how can I make progress in the functional? Where did I put the functional? So remember, this was like this functional E of mu. So you can think of it as kind of a steepest descent algorithm that tries to say, how can I move as little as possible with respect to the Wasserstein metric while making as much progress as possible with respect to this functional, right? So this is, in the limit, this is the equation, the partial differential equation that you get. Okay. So at this point, there are two main questions. And then we're going to conclude. So there are two important questions, maybe that we can focus. The first one is, what can we say about the convergence? So what is the convergence of this PDE to global minimizers of the functional? And the second one is how useful or how so how useful is this dynamic with respect to the number of particles, to the number of particles. Okay? So we're going to see this, exactly what we meant in a second. Okay, so for the first one, so remember, right? So here we have a formalism that is a PDE, that is the PDE that describes the behavior of basically the locations of the particles. And this PDE is valid even for measures that have no regularity. For example, measures that are really the empirical measure, right? Like the measures that look like this, right? But unfortunately, what would be like a classical, like a good answer for this one? The typical in PDEs is say, okay, if the initial condition satisfies certain properties, then the PDE under this initial condition converges to where I want. So do we have this kind of result? Knowing that in our case, the initial conditions must look like that, right? They must look like a bunch of Diracs, right? So unfortunately, the kind of results that we have for one, so I'm going to just list one that, and in a sense, it captures many of these papers. So the one from Shizambak, and then there's another one that also gets some global convergence, that is the Rotzkopf and van den Eyden. That essentially says that if mu0, so like the initial density at m0, is sufficiently smooth and diverse, so in other words, if it has mass at enough places, like it's sufficiently smooth, and mu t converges to something, so this PDE converges to some mu infinity, then E of mu infinity, like n mu infinity, is a global minimizer of E. Okay? So basically, these kind of results, so these papers, they really took some, like basically used this formalism to culminate. They basically use it and understood under which conditions you can use this formalism to derive global convergence. But of course, there's an important caveat, or there's an important point here that, in a sense, goes back to what is the title of the lecture, that is the mean field, right? So what does it mean here, mean field? In fact, we can see that we have two tools. So there are two tools that we can use to transform a measure. So there's one. So from an initial distribution mu0, right, we can obtain a bunch of samples, right? We can sample from that distribution, and this creates our initial model, right? So we can sample, and we obtain, like I would say, like the empirical version, which is 1 over m of delta theta I with theta I that are drawn IAD from mu0. Right? So in your mind, once I have a measure that is like very smooth, I can sample and get like a bunch of Diracs, like kind of an empirical version of the measure. Right? Then the other thing that we have described here, I can also modify the measure by running this PDE, so kind of like turning time. Right? So I could now think about the PDE with this initial condition. So I run the PDE, right, for t units of time, and I will get mu t. Right? I could also run the PDE from this equation for t units of time and get maybe u 0m, I don't know, like t. Okay, there's like 3 indices. Sorry. It would be like tm. Okay? So what would be the natural question that you would like to happen? So I have a diagram, right? Does this diagram commute? So in other words, once I have this measure, if I sample, do I get something that looks like this? No. In general, no. And there's one way to convince yourself that that cannot be the case. Think about the independence, right? So here at time 0, all these particles are independent, right? I just draw them to be independent. Once I let the dynamics evolve, right, we just see it, right? Like the evolution of a measure basically depends on where the rest are, right? That's the nature of the interaction. But there's a very powerful paradigm in statistical mechanics that despite the fact that these things and these things are not the same, at leading order, they are the same. In other words, the error that you make at finite times is smaller than m. It's basically going down with m. So in other words, morally, you can almost consider the evolution of the particle. You can interpret or you can study the measure that you would get by running the PDE in the empirical world after t units of time as morally the mean. So this is what's called like the mean field solution, right? So the mean field is basically the regime in which you take the number of particles to the infinity. So you can actually morally assume that this diagram commutes. And this is what's called, in statistical mechanics, the argument that is called like a propagation of molecular chaos. Okay, and this is an interesting aspect because in some frameworks, it has been formally proven, right? So you can actually rigorously establish, really control the gap between these two things, right? And for example, there's so there are many frameworks beyond the context of neural networks where this formalism has been established. And so, in fact, there's actually, and related to that, there's a non-quantitative version of this story that basically says that, and this is another theorem by Shiza and Bach, and also the paper by May, Montanari, and Nguyen, that basically says that in the limit, t going to infinity, these two objects commute. So in other words, under the assumption that we have before, so under previous assumptions, then the limit commute with m and t going to infinity of the energy of m and t is actually the mean of energy. Okay? So the quantitative version, I have to insist in finite times. So like actually showing the rate of convergence of this thing is open right now. And then there's some refinement. There's some several papers that exploit several aspects. But this is one of the, let's say, outstanding questions. Okay, so.
Is it the hat? Is the
Yes.
bottom icon?
Correct. So this is like this would be, you start from here. So this is what the algorithm can do. You run dynamics, and this thing certifies that if m is sufficiently large, these two trajectories are going to basically track each other.
Do MNT grow at some particular rate?
Rate? No, the rate is actually open. So there's some arguments. So Montanari, so this paper, they get rates, but they're exponential in time. So in other words, if you want to make, so t, like m has to grow much faster than t. Okay? Okay, so as kind of concluding here. So as concluding remarks, we have seen that, especially today, in particular, we have seen two asymptotic regimes of large neural networks. It's called like the lazy regime. So in one case, let's say the model here is 1 over m, the sum of functions. And here what we saw is that the canonical way to scale to get this lazy regime is to use 1 over square root of n. Right, so that's for the model. Here what we know is that if we think in terms of the initialization, right? The initialization here is 1 over square root of m. And here it would be like 1 over 1, right? So here, in other words, the models, they are scaled by a factor of square root of m at time 0, the fluctuations. So what we saw, like the relative scale, so this k times m, here we define this regime such that the relative scale does not change with m. Here the relative scale is 1 over square root of n. And importantly, like the displacement in parameter space. So basically this would be like the time, the parameter at time 0 minus the parameter at time infinity. Here we have a model, there's a framework where this PD at the limit, right, when m goes to infinity, things move, the mass moves, right? It moves according to these dynamics, right? So things really move. Whereas here, we have seen that basically the scaling of this displacement goes to 0 at the rate that depends on basically the larger the model, the less displacement we have. And this is a table that I borrowed by a nice presentation by Lennik that he gave recently. Okay, so this comes from his conclusion. So one of the things that we can conclude is, in a sense, that at least the mean field regime is a framework that, at least in the context of a single hidden layer, it explains things in a way that are kind of satisfactory, right? So in particular, it explains why we can learn while moving in parameter space. So it really has this property to actually learn while choosing the right features, right? So not just using the features that you give initialization, I actually move until I find the right features. Okay, and so one of the things that is open, right, is that how to extend to deep architectures, to deeper architectures. Okay, so it's a framework that essentially plays very well when you have a single hidden layer, because it's really like the fact that you have an average of functions. But it's not obvious how to extend it to deep architectures. There's many other properties like you can really push tools from optical transport to get like better rates, to get a better understanding. So things like, for example, like the displacement convexity is something that you can use to get like better rates. But just as I wanted to conclude with really one of the take-home messages that I think is important, there is this notion of like, what does it really mean, this notion of overparameterization? Versus like this overfitting, right? Or like this idea that because I have a model that is very large, and I just, how come this very large number of parameters are not trapping me, like finding solutions that are very poor generalization? So how can we have this kind of mystery? And in a sense, what we have seen is that overparameterization, like the fact that I have many parameters, is not necessarily related to the fact that I have a larger complexity model, right? And therefore, a bigger chance of overfitting, right? We have seen actually different stories where I can perfectly let the number of parameters go to infinity, and the algorithm is going to choose solutions that have control complexity, control norm, right? And so really, this is one of the things that I would like for you to take home, is that once you think about what is the responsible for overfitting, for the fact that I'm like, maybe going to have a big gap between training and test, is really the complexity of the function that I'm learning. And this is actually a story that is only partially captured by the number of parameters, right? As you can see here, we are really working in infinite dimensional functional spaces, right? And still we can generalize. And so there are many, of course, open questions that I didn't have time to talk about. In particular, formalizing this, like making this diagram a bit more formal and with more rigorous is one of the things that is, I think, particularly interesting. The other one, of course, is to get like what is the corresponding functional space when you have a deeper architecture, in particular using maybe focusing on the case where you have convolutional structure, right? Not just a deep architecture without structure. That's another important challenge for the future. So with that, thank you very much. And yeah, I've been great.